The last meeting was disconnected due to some unknown reasons. So we'll continue from here. We discussed about some of the points about the current, right? Some of the important points about the current. And you can see that this is the question here. The question is current I is equal to 2 plus 40 ampere, right? Where T is in seconds, is flowing through a wire for 2 seconds, right? The question is find out amount of charge flown through the wire, right? We have to find the amount of charge flown through the wire, right? For 2 seconds, right? So I is equal to 2 plus 40, right? We can write this current as, we can write it as dq over dt, right? dq over dt, that will be equal to 2 plus 40, right? Now dq will be equal to 2 plus 4t gt, right? Integrating on both sides for time t equal to 2 seconds. So we'll integrate it from 0 to 2 seconds, 0 to q, right? So delta q will be the total charge flown, right? We'll integrate it for integral of 2 plus 4t dt. We can write it as 0 to 2 dt, right? Plus integral of 4t dt, right? With limits 0 to 2, right? So here the total charge flown will be 2t 0 to 2, right? Plus 4 upon 2 t square with limit 0 to 2, right? So the total charge flown will be 2 times 2 minus 0, right? Plus 2 times 2 square minus 0, right? So it will be equal to 4 plus 8. That will be equal to 12 coulombs, right? So 12 coulomb will be the total charge flown during this time, right? What we did is that we differentiated, we just represented current with dq upon dt, and then integrated the charge on both sides, right, to get the total charge flown through the time 0 to 2 seconds, right? So let's discuss another question here. The question is that a current flows through a cross section of 20 centimeters square for 20 milliseconds. Find out number of free electron crossed through that area, right? We have to calculate the number of free electrons crossed through that area, right? So the time for which the current has flown is given as 20 milliseconds, right? That's 20 milliseconds. Or we can write it as 20 into 10 to the power minus 3 seconds, right? That's equal to 2 into 10 to the power minus 2 seconds, right? So this is the time for which the current has flown through the cross section of 20 centimeters square, right? So the current will be, that will be charge upon time. Delta q is the charge and delta t is the time, right? We don't know delta q, that's upon delta t, right? Find out number of free electrons. A current flows 20 ampere current, right? It's given that 20 ampere current flows, right? Not a current, it's 20 ampere current, right? 20 ampere current. So current is given as 20 amperes, right? 20 amperes. We can just substitute the value of I with 20, right? 20 multiplied by delta q upon delta t, that's 2 into 10 to the power minus 2, right? The charge flown will be nothing, that's equal to 20 into 2 into 10 to the power minus 2 coulombs, right? Or we can write it as 0.4 coulombs, right? 0.4 coulombs. So 0.4 coulombs is the charge flown through this cross section during the time 20 milliseconds, right? During the time 20 milliseconds. It means that, but we have to calculate the number of electrons, find out the number of free electrons crossed through that area. We know that charge, by quantization of charge, delta q is nothing, is the integral multiplier of this electronic charge, that's Ne, right? And this delta q is 0.4 coulombs, right? And E is the electronic charge, that's equal to 1.6 into 10 to the minus 19 coulombs, right? Now we can get the number of electrons, and that will be equal to 0.4 upon 1.6 into 10 to the power minus 19 coulombs, right? So we can just put the value here, right? So it will be 0.4 upon 1.6 into 10 to the power 19, right? Or we can write it as it will be 4, that will be 1 upon 4, that's 0.25, right? Into 10 to the power 19, or we can write it as 2.5 into 10 to the power 18 electrons, right? So these number of electrons will be flowing through this conductor in the time t equal to 20 milliseconds if the current flowing through the conductor is 20 amperes, right? So these are the number of electrons flown through the conductor. Let's have another question here. The question is that in a discharge tube, 3 into 10 to the power 18 electrons, right? It's actually 3 into 10 to the power 18 electrons. So these much of electrons are flowing per second, right? From right to left. From right to left, it means from right to left here in this discharge tube, there are 3 into 10 to the power 18 electrons are flowing per second. So it means that time has been given as 1 second, right? 1 second is the time for which these charges are flowing. And at the same time, 2 into 10 to the power 18 positive ions, right? 2 into 10 to the power 18 positive ions per second are moving from left to right. They are moving from left to right, right? So then find current through the discharge tube. We have to find the total current through the discharge tube, right? Now the total current will be the current due to these negative charges and the current due to these positive charges. So that will be the total current, right? We can see that the negative charge is flowing in this direction. If negative charge is flowing in this direction, the current due to negative charge will be along this direction. Let me call this as IE. And if the positive charge is flowing in this direction, then the current because of this positive charge will be I plus in the same direction along the direction of the positive charge. And we know that for the negative charge, the direction of current is opposite to the direction of positive charge. The direction of current is opposite to the direction of negative flow of negative charge, right? So it means that we can just calculate the total current as this is the current in this direction, right? Two currents are in the same direction, IE and I plus, they are also in the same direction. It means that the total current I will be nothing, that will be equal to IE plus I plus, right? It means that current because of this positive charge and the current because of this negative charge, right? So total I will be equal to, the charge flown is 3 into 10 to the power 18 electrons per second, right? So 3 into 10 to the power 18 electrons. So electronic charge will be 1.6 into 10 to the power minus 19, right? And the time is 1 second, we can just divide it by 1. And similarly for positive charge, the charge will be equal to 2 into 10 to the power 18 multiplied by 1.6 into 10 to the power minus 19, and the time is the same, 1 second, right? So it will be nothing, it will be 5 into 1.6 into 10 to the power 18 into 10 to the power minus 19, right? So it will be nothing, that will be equal to 5.65 into 1.6 will be equal to 8, right? And 10 to the power 18 into 10 to the power minus 19 will be 10 to the power minus 1, or we can write it as 0.8 amperes, right? So it means that 0.8 ampere will be the current flowing through this discharge tube because of the flow of negative charge from right to left and because of the flow of positive charge from left to right. So this will be the total current. So let's move on to the next question here. In this question, we have been given that an electron revolving on a circular track. You can see that there is an electron revolving on a circular track of radius 1.6 centimeter with a constant speed of 3.40 into 10 to the power 6 meter per second. We have to find the current flowing in the circle, right? So here also you can see that the electronic charge is moving in a circular path, right? And because of the movement of this charge in a circular path, there will be a current because of this, right? So we have to find this current, right? Once again, the current will be nothing, it will be equal to the charge upon time, right? current will be nothing, the charge upon time, and the charge is nothing, it's the electronic charge, right? That's electronic charge upon the time. And the question is, we don't know about the time, right? You can see the total time taken by this electron to complete this circle. To complete this circle will be nothing. It will be time t. That will be the circumference of the circle. That's 2 pi r, right? Upon the speed of this electron. Let's suppose that's v, and it's given that 2 pi r. R is the radius of this circle, and it's given as 1.6 centimeter. We can write it as 1.6 into 10 to the power minus 2 meters, right? Upon the speed of this electron, speed of this electron is given as 3.14 multiplied by 10 to the power 6 meter per second, right? So that's the value of the speed of this electron. And we can see that pi value of pi is nothing. It's equal to 3.14 approximately, right? That means that we can just cancel out this pi with 3.14, right? So our time will be nothing. It will be equal to 2 into 1.6 will be 3.2, right? And it will be 10 to the power minus 8 seconds. So it's a very small time, right? 3.2 into 10 to the power minus 8 seconds. So let's put that value of time in the above equation of current, right? The charge is the charge of electron. That's 1.6 into 10 to the power minus 19 upon the time t. That's 3.2 into 10 to the power minus 8, right? So this will be cancelled with 2, right? Will be left here with 0.5 into 10 to the power minus 19 multiplied by 10 to the power 8, right? So it will be approximately, it will be almost equal to 5. It will be equal to 5 into 10 to the power minus 12 amperes, right? 5 into 10 to the power minus 12 amperes. So this will be the correct, because of this electronic charge which is moving in a circular path, right? What we did in this question is that the charge that was flowing in the circular path was the electronic charge, and the time was the time taken by this electron to complete the whole circle, right? Which was going with a speed of 3.14 into 10 to the power 6 meter per second. And we calculated the time using the velocity or the speed of this electron, and we got that time equal to 3.2 into 10 to the power minus 8. That's circumference upon the speed of electron, and substituting the value of time in this current equation to get the value of current, right? So let's discuss another question here. The question is a graph of a current carrying wire versus time is given, right? We have been given a graph of a current carrying wire versus time. Find out the amount of charge flowing through the wire in time interval t equal to 2 seconds to t equal to 12 seconds. So you can see clearly in this picture that we have been given a graph or a plot between the current and the time, right? And the plot runs from 0 to 12 seconds, right? You can see that the plot runs from time t equal to 0 to time t equal to 12 seconds. But the question is that we have to find the amount of charge flowing through the wire in the time interval t equal to 2 seconds to t equal to 12 seconds, right? So we know that current is nothing, instantaneous current is nothing, it's equal to tq dt, right? Tq dt, or you can write this tq as idt, right? Idt. If we integrate it on both sides, right? And this is nothing, this is the area under IT graph, right? Current time graph. If this represents area under current time graph, it means that the charge flow between the time interval t1 to t2 will be just given by the area under this curve between the time interval t1 to t2. So that will be the charge flow. So delta q will be nothing. It will be integral of t1 t2 idt, right? Since we have not been given any function, right? But still we can just calculate the charge flow using the concept of area under the curve, right? So area under this current time graph between the interval time t1 to t2 will give us the charge flow in that interval, right? So the interval here is time t equal to 2 seconds and time t equal to t1 here is 2 seconds and t2 here is 12 seconds, right? 12 seconds. So between the interval of, in the interval of 10 seconds, we have to find the current. So it is between t equal to 12 seconds and t equal to 2 seconds. So this will be the area enclosed by this graph. So this much will be the area, right? Right, this will be the area. So you can see that this area here is a rectangle, right? This is a rectangle here, and this is nothing, this is a trapezium, right? Trapezium. the total area will be the area of rectangle here plus the area of trapezium, and this total area will give us the total charge flow between the interval time t equal 2 seconds and 12 seconds, right? So total area will be area of this triangle, and you can see that the area of this triangle will be nothing. The length here is 6, right? And the height of this triangle from here to here is 5, right? So the area will be equal to 6 into 5, right? Plus, for trapezium, the area is nothing half of sum of parallel sides. Sum of parallel sides, these two sides are the parallel sides of the trapezium, right? From here to here, the length is 5. From here to here, the length is 10. So it's nothing, it's 5 plus 10 multiplied by the perpendicular distance between them. We can see the perpendicular distance between the two parallel sides of a trapezium is like this. This is the perpendicular distance, right? And we can see that this perpendicular distance is nothing. This is 12 minus 8, that's equal to 4. So we'll just multiply it by 4 here, right? So 6 into 5 will be 30 here, right? Plus half multiplied by 50 multiplied by 4, right? So it will be equal to 60 coulombs, right? 60 coulomb. So 60 coulomb will be the total charge flow between the interval 2 seconds and 12 seconds. So that's how we calculate the charge flow. If we have to calculate the total charge flow, right? If the total charge flow has to be calculated, that will be from 0 to 12 seconds. Total charge flow, that will be equal to 0 to 12 seconds. It means that we have to just add this triangular area to this 60 coulomb charge, right? And this triangular area will be nothing. You can just calculate this triangular area as half base into altitude. Base is 2 and the altitude is 5. So 2 into 5, right? So this 2 and 2 will get cancelled. The total charge will be 60 plus 5. That will be equal to 65 coulombs, right? So this will be the total charge flow for this question, right? So let's move to the next slide here, right? So we'll be here in this slide classifying the conductors or the materials based on their conductivity, right? Conduct based on the conductivity of the materials. We classify the materials into three types, right? One is the conductors, another is the insulators, and the third one is semiconductors. And you know that in case of conductors, we call those materials as conductors where the electrons are freely available for the conduction, or we can say the electrons are loosely bound to it so that they are easily available for the conduction of electric current. So these electrons are almost free, right? These are almost free. They are very loosely bound to the material atoms of the material. That's why they are freely available for the conduction, and such materials we call as conductors, right? And similarly, we have insulators where all these electrons are not available for the conduction. They are not freely available for the conduction, and they are very tightly bound to the molecules of a material, and that's why we call these materials as insulators. And third type is semiconductors. So semiconductors are the materials, right? These materials behave like the conductors at high temperatures, and they behave like the insulators at low temperatures, right? Because of the fact that when the temperature of the semiconductors are increased, their resistance decreases. Because of the decrease in the resistance, the conduction of the semiconductors increases, or the flow of current through the semiconductor materials increases. And similarly, if we decrease the temperature, the conductance or the flow of current through the semiconductors decreases, right? If we decrease the temperature, right? So that's the reason we call these as semiconductors, right? Their conduction lies between that of insulators and the conductors. So at high temperatures, they conduct a good amount of electricity, right? And at low temperatures, the resistance of the semiconductors increase, and they no longer conduct at low temperatures, right? So this was the classification of materials on the basis of conduction or the conductivity. We classify them into three types of materials. One is conductor, another is insulator, and the third one is semiconductors, right? But in this chapter, we'll not be discussing about the insulators. You know that insulators are sometimes we also call that insulators as dielectrics, right? Which we studied in the electrostatic portion, right? In insulator, what happens is that we study that in case of electrostatics that polarization takes place, right? Polarization, we mean that the charge is induced because of the external electric field in the insulators, but those charges are not freely available for the conduction, right? So because of even if the insulators may be negatively charged or positively charged, or insulators may have some polarization, but those charges are tightly bound and they are not available for the conduction, right? So we call such materials as insulators, or sometimes we call them as dielectrics as well, right? So that's it for with respect to the classification of conductors, right? In the next lecture, we'll be discussing different properties of electric current, and we'll be also discussing about the microscopic form of Ohm's law, right? We'll be discussing the different concepts of the current, right? We'll be discussing the microscopic form of Ohm's law in the next lecture, right? So that's it for today. Till then, take care and goodbye.